So for a matrix, a square matrix, so if we've got A and Fn, n, this matrix is diagonal if it has no non-zero entries off the diagonal. So in other words, when j and k are different, ajk is equal to 0. So the only non-zero entries you can have are on the diagonal. And so the idea is that if A is the matrix of some operator t, and it looks like a diagonal, so let's say it's got lambda 1 through lambda n down the main diagonal like this, and it's 0 everywhere else, and I'll just leave the other everywhere else blank to indicate the zeros. So if this is with regard to the matrix of this operator in the basis v1 through vn, then each vk is an eigenvector. And I should say actually that it's a lambda k eigenvector. It's an eigenvector corresponding to lambda k. And so the way to see this is just to say, okay, if we've got lambda 1 da 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 da, lambda k da 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 da, lambda n, and we're in the basis v1 through vn, then the matrix of this vector in with respect to this basis is going to have a 1 and then all be zeros, and so on and so forth. So this one is going to be zeros all the way until the last one where there's a 1, because we're that's how you represent that vector with respect to that basis. So if we look at the matrix corresponding to the vector vk, it's going to have a 1 in the kth spot and zeros everywhere else. And so the way the entries line up when you do matrix multiplication, you're going to get 0 for every single entry except in the kth one, where you'll have 1 connecting. So this 1 will connect with this lambda k right at that point, and so you'll get a lambda k, and then everywhere else you'll have zeros again. And so this is lambda k times vk, right? Okay, so that's the idea. So we're going to be looking at diagonalization, meaning when is it possible to put a matrix in diagonal form, or in other words, find a basis in which the matrix of the operator is diagonal. So if we've got a scalar lambda, which is an eigenvalue of an operator t, then the eigenspace of t corresponding to lambda is, let's see, and so the book writes it as e lambda t. I prefer to write it with a subscript, and most of the time I prefer to not even bother mention the transform, because typically we only talk about the eigenvalues of one operator at a time. It's uncommon to have two different operators and be talking about their eigenvalues simultaneously. Sometimes you do it to compare them back and forth, but most of the time it'll be good enough just to write e sub lambda. And so the actual definition of e sub lambda is that it's the null space of t minus lambda I. And so this is all of the elements of V that satisfy the eigenequation. And so those are the eigenvectors, let me just specify lambda eigenvectors, together with 0, because 0 is not an eigenvector. So we have to throw it in on the end. Okay, so notice then that if we take T and we restrict it to the lambdath eigenspace, then when we apply it to V, some element from the lambdath eigenspace, then it just scales by lambda. And so in the example above that I drew out, you can see that V looks like the eigenspace for lambda 1, and then we have a direct sum that goes through all the different distinct eigenvalues. And we have that T restricted to E lambda K is going to just scale vectors of that space by K. So what we have is we have a decomposition into invariant subspaces. And so the question is, does this always happen? Spoiler alert, no, it doesn't always happen. This is the question of whether or not a matrix can be, or an operator can be diagonalized.